Monoidal categories and their representations, Lecture 16, Hopf algebras. Let us start by recalling the classical definition of an algebra. Let K be a field. An algebra over K is a tuple A, M, and U, where A is a K vector space, M is a linear map from A tensor over Ka to A, and U is a linear map from K to A. This datum is supposed to satisfy the following axioms of associativity and unitality, expressed as commutativity of the following diagrams. The first diagram represents associativity. If we start from A tensor over Ka tensor over Ka, we can use identity tensor M to go to A tensor over Ka, and then M to go to A. Alternatively, we can use M tensor identity to go from A tensor over Ka tensor over Ka to A tensor over Ka, and then we use M to go to A. So this diagram should commute. These two ways should coincide. So this expresses the associativity of our multiplication map M. And then we have the unit map U from K to A, and this is supposed to satisfy the following two conditions: unitality axioms expressed by the following two diagrams. Starting from A, we have the canonical isomorphism between A and K tensor over Ka. Now we can use U tensor the identity to go to A tensor over Ka, and we can use the multiplication to go back to A. So this composition should coincide with the identity map on A. And similarly on the other side, we start from A, we use the canonical map to A tensor over K. Now we use identity tensor U to go to A tensor over Ka, and we use multiplication to go to A. This composition should coincide with the identity map on A. So this is the classical definition of an algebra over K. The dual notion to an algebra is the notion of a coalgebra. So a coassociative and counital coalgebra over K is a tuple which consists of a K vector space C, a linear map delta from C to C tensor over Kc, and a linear map bold C from capital C to K. And this datum is supposed to satisfy the following axioms, the coassociativity and the counitality axioms, which are expressed as commutativity of the following diagrams. So first, the coassociativity axiom. Starting from C, we use the comultiplication delta to go to C tensor over Kc, and now we apply delta at the first component to go to C tensor C tensor C. Alternatively, we start from C, we comultiply to go to C tensor over Kc, and now we use delta on the second component to go to C tensor C tensor C. So this diagram should commute. This is the coassociativity axiom, and here are the two counitality axioms. Starting from C, we comultiply to C tensor over Kc. Now we use the counit at the first component to go to K tensor over Kc, and this is isomorphic to C via the canonical map. And this composition should coincide with the identity on C. And similarly for the second component. So we see that the definition of a coalgebra is really dual to the definition of an algebra. Let us phrase this duality observation more precisely. Let us denote by star the usual vector space duality, which is homing over K into K. This duality is a contravariant endofunctor of the category of all vector spaces over K. And it is a contravariant autoequivalence of the category of all finite dimensional vector spaces over K. And the duality between algebras and coalgebras is expressed as the following mathematical claim. If a tuple A, M, U is an algebra, then the corresponding tuple A dual, M dual, U dual is a coalgebra. Conversely, if the tuple C delta and the bold C is a coalgebra, then the corresponding dual tuple C dual, delta dual, C dual is an algebra. So since the duality is contravariant, inverting all arrows, it swaps the associativity axiom with the co-associativity axiom, and it swaps the unitality axioms with the co-unitality axioms. So since our duality is an autoequivalence of finite dimensional vector spaces, then if A is a finite dimensional algebra, then taking the second dual, we will get A as an algebra. And similarly, if we have a finite dimensional coalgebra, then taking the duality twice, we get the same coalgebra back. Now let us talk about bialgebras. So these are algebras and coalgebras at the same time. A bialgebra over K is a tuple which consists of 5 components, B, M, U, delta, and C. So B is a vector space over K, M is a multiplication, U is a unit, delta is a co-multiplication, and C is the co-unit. So here, B, M, and U should form an algebra, and B, delta, and C should form a coalgebra. And these two structures should be coordinated by the following compatibility axioms. So first of all, starting from K, we can go by U to B, and then we can go by C to K back. So this composition should be the identity map on K. The second diagram, starting from B tensor B, we can multiply into B and then use the co-unit to go to K. Alternatively, we can use the co-unit at each of the components of B tensor B to go to K tensor K, and then we can use the canonical map to go to K. This diagram should commute. Here are two other compatibility diagrams. So if we start from K, we can use the unit map to go to B, and then the co-multiplication to go to B tensor B. Alternatively, we can use the canonical map to go from K to K tensor K, and then we can use U tensor U to go to B tensor B. This diagram should commute. And finally, we have the following commuting pentagon diagram. Starting from B tensor B, we can multiply to go to B, and then co-multiply to go to B tensor B. Alternatively, we can apply delta tensor delta to go to B tensor B tensor B tensor B. Then we swap the second and the third components of this big tensor product. We denote the corresponding map by tau. So we again go to this tensor product B tensor B tensor B tensor B. And now we multiply the first two components and the second two components, and we go to B tensor B. So as already mentioned, here tau is the map on B tensor B, which just swaps the two components of the tensor product. So this is the symmetric braiding on the tensor product of K vector spaces. So this is the final axiom for the definition of a bialgebra. Here is an example. Let G be a group with multiplication given by dot and with the identity element E. Consider the group algebra of this group. This is a unital algebra with respect to the unit map, which sends the element 1 in our field to the identity element in the group, and the multiplication map induced by the product in our group. Define the co-multiplication delta as follows. Delta of G is equal to G tensor G. So since group elements form a basis in B, this can be uniquely extended to a necessary linear map which defines the co-multiplication. Define the co-unit map as follows. The value of the co-unit map at each group element is equal to 1. Again, since group elements form a basis, this uniquely defines the co-unit map as a linear map. And then one can check that all axioms are satisfied. So here is an example of checking the big compatibility diagram, the last pentagon axiom for the bialgebra. So if we start from the element G tensor H, and such elements form a basis in B tensor B, so we only need to check the diagram on these basis elements. If we multiply, we go to GH, and this is again a group element, so if we co-multiply, we go to GH tensor GH. Alternatively, if we co-multiply both G and H, we go to G tensor G, tensor H tensor H. This is directly from this definition. Now we swap the G and H in the middle, so we get G tensor H tensor G tensor H. And now we multiply here, we go to GH, and we multiply here, we go to GH. It's a nice exercise to check all other axioms of a bialgebra. So the group algebra of G over K is indeed a bialgebra. Let us now discuss how we can extend algebra structures to tensor powers. Given an algebra A, M, and U, we can consider the algebra where the underlying vector space is a tensor product of A with itself over K, and we have the multiplications M tilde and the unit map U tilde defined as follows. The unit map is just the composition of the canonical embedding of K into K tensor K with the tensor product of the unit map U with itself. So this goes to A tensor A. So this is the unit map U tilde for the bigger algebra. And the multiplication map M tilde is defined as follows. So we start with the tensor product of A tensor A with itself. We use our braid in tau here in the middle to swap the parts in positions 2 and 3. So we end up in A tensor A tensor A tensor A. And now we multiply the first two components and the last two components, and we end up in A tensor A. It is very easy to check that this defines on A tensor A with this M tilde and U tilde that this is indeed an algebra over K. So in particular, the consequence is that if we apply M tilde to the pair of elements x1 tensor y1 and x2 tensor y2 in this tensor product, then the outcome will be the product of x1 and x2 under the multiplication M from the original algebra A, tensor product with the product of y1 and y2 under M. Similarly, one can extend the coalgebra structures to tensor products. Given a coalgebra C delta and then bold C, we can consider the coalgebra given by the tensor product of the original C with itself over K, and the comultiplication delta tilde and the counit map bold C tilde, where the counit map is the composition of the following two maps. So we start from C tensor C, we apply bold C tensor bold C to go to K tensor K, and then we use the canonical isomorphism to contract this to K. And delta tilde is similarly the following composition. We start from C tensor C. We use delta tensor delta to go to C tensor C, tensor C tensor C. And then we use tau in the middle to swap the two components here, component 2 and component 3. And we end up in C tensor C tensor C tensor C. And it is easy to check that this defines a coalgebra. This is simply the dual definition to that of an algebra on the tensor product. Now let us look closer at the bialgebra axioms. Let B, M, U, delta, and C be a bialgebra. Then delta is an algebra homomorphism and M is a coalgebra homomorphism. Recall that delta is a map from B to B tensor B. Now B is an algebra by definition, and we just said that we have a natural algebra structure on B tensor B, which was defined 2 slides above. So the claim is that one of the bialgebra axioms says exactly that our comultiplication map delta is an algebra homomorphism from B to B tensor B. And similarly, our multiplication map is a coalgebra homomorphism from B tensor B to B. So we check the first claim, and the second claim is similar. If we look at our last pentagon diagram, so we see exactly, so we have the multiplication here from B tensor B to B, and now the composition of these two maps, this is exactly the definition of the multiplication on B tensor B. And now we have delta here and delta tensor delta here, which says that the delta map intertwines this multiplication with this multiplication. So this says exactly that delta is a morphism of algebras. And on the same diagram, we see that M is a morphism of coalgebras. Also, if we look at the following diagram, so here we have U tensor U, delta, and the canonical map. So this says exactly that delta intertwines U and U tilde, which is defined as a composition of the canonical map and U tensor U. So now we are ready to define the notion of a Hopf algebra. Definition: a Hopf algebra is a tuple which consists of H, M, U, delta, C, and S, where the tuple H, M, U, delta, C is a bialgebra, and S is a linear map from H to H. And this linear map should satisfy the following axiom: the following diagram should commute. If we start from H, we can use the co-unit to go to K, and we can use the unit to go to H back. Alternatively, we can co-multiply to H tensor H, and then we can use our linear map S at the first component to go to H tensor H, and then we multiply to go to H. Yet another alternative is to co-multiply to H tensor H, and then use S at the second component, and then multiply back to H. So this diagram should commute. And the terminology, the linear map S, is called the antipode. Here is an example. Let G be a group. Then we have already seen that the group algebra of G over K is a bialgebra. And then the claim is that this bialgebra structure can be extended to a Hopf algebra structure by defining the antipode as follows. The value of the antipode, the group element, G, is defined as G inverse. And this uniquely defines a linear map because the group elements form a basis of our H. So let us check our big axiom. So if we start from an element G, so it's enough to check this axiom on the basis. We take a basis element G. The co-unit sends G to 1, and the unit map sends 1 to E. Alternatively, the commultiplication sends G to G tensor G. The antipode on the first component inverts G into G inverse. And then the multiplication sends G inverse tensor G to G inverse times G, which is the identity. And similarly for the third pass in this diagram. Here's another example. Assume that the characteristic of a field K is not true. Let G be a Lie algebra over K. Consider the universal enveloping algebra U of G. Note, this algebra is already a unital associative algebra. So we define the commultiplication in the following way. So delta applied to an element G in G is equal to G tensor 1 plus 1 tensor G. The counit map sends all elements from our Lie algebra to 0. And the antipode map sends all elements in our Lie algebra to minus the corresponding element. The claim, this defines on U of G the structure of a Hopf algebra. Note that delta, C, and S should be extended from G to the universal enveloping algebra, so they are only defined on the elements of G. And one can do this using the facts that delta and C are algebra homomorphisms, while S is actually an algebra anti-homomorphism. And noting that the Lie algebra G generates the universal enveloping algebra as an associative algebra, so it follows that this definition actually gives a well-defined map on the whole of U of G. So here is a brief summary of properties of a Hopf algebra. Assumes that we have a Hopf algebra H with multiplication M, unit U, comultiplication delta, counit C, and the antipode S. We already mentioned that delta is an algebra homomorphism, and also C is an algebra homomorphism. The multiplication M is a coalgebra homomorphism, and similarly U is a coalgebra homomorphism. The map S, the antipode, is an algebra anti-homomorphism, and it is also a coalgebra anti-homomorphism. So the first four properties here, they follow directly from the axioms, and the last two properties, they require proof, and this is a good exercise. One can check the following link to a web resource or the book of GNOME. And another note is that an antipode on a bialgebra is unique if it exists. So being a Hopf algebra is a property, additional property of a bialgebra, not an additional structure. Let us now discuss modules over Hopf algebras. Let H be a Hopf algebra. Consider the category H mod of all modules over the algebra H, M, U. Given two H modules M and N, their tensor product is obviously a module over the algebra given by tensor in H with itself. It's just the first H acts on M and the second H acts on N. So tensor product of two H modules is naturally a module over the tensor product of H with itself. But now the Hopf algebra structure has the comultiplication, and this comultiplication is an algebra homomorphism from H to H tensor H. Therefore, we can view the tensor product of M and N as an H module via this homomorphism. So H acts on U as delta of H acts on U for H in H and U in our tensor product of M and N. Also, we can view the base field K as the quotient of the regular H module via the algebra homomorphism given by the counit map. So now we have one very special module over H, which is K, given by the counit map, and we can actually tensor H modules with each other. This defines, on the category of all H modules, the structure of a monoidal category, where the associator and the unitars are inherited from the category of all K vector spaces. And of course, the category of all finite dimensional H modules is a monoidal subcategory of the category of all H modules. And here, so far, we didn't use actually the antipode, so this works equally well for all bialgebras. The existence of the antipode is necessary if we want to address the question of rigidity. So let H be a Hopf algebra with an invertible antipode S. then the claim is that the category of all finite dimensional H modules is a rigid monoidal category. Proof: let V be a finite dimensional H module. Consider the dual of V, just the dual vector space, then this is naturally a right H module. But we have an antipode which is an anti-automorphism of the algebra H. So we can consider the right H module V star as a left H module by twisting the action of H on V star using this anti-automorphism. And then we have the natural adjunction morphisms for the pair V dual comma V, which are inherited from K mod. And from the antipode axioms, it follows that these are actually morphisms of H modules. And in particular, this pair is a pair of adjoint objects also in the category of all finite dimensional H modules. So all the axioms allow us to see that the category of finite dimensional H modules inherits from K mod the structure of a rigid monoidal category. So here is an extended example. Let K be a field of characteristic different from 2. Consider Svidler's Hopf algebra over K, which is given by the following presentation as an algebra. So the algebra H is generated by two elements X and C squares to the identity, X squares to 0, and C and X anti-commute. From here, we immediately see that the basis of this algebra is given by the identity C, X, and Cx. The commultiplication is given as follows. So delta of 1 is 1 tensor 1, delta of C is C tensor C, just like in a finite group, and delta of X is C tensor X plus X tensor 1. So this is a bit strange. The counit map sends C to 1, just like in a finite group, and X to 0, like in the Lie algebra. And the antipode sends C to C, note that C squares to the identity, so C is equal to C inverse, and it sends X to minus Cx. This is a very strange formula. And one can check that all this defines on H the structure of a Hopf algebra. Note that this is neither commutative because C and X, they anti-commute, they do not commute. And it is not co-commutative because of this very strange formula for delta of X. So this is a very strange Hopf algebra. The elements X and Cx generate a nilpotent ideal. So X square is 0 and Cx square, there will be some Xc which we can commute up to sign, and then we get X square, which is again 0. So both these elements are nilpotent, and clearly if you multiply with X or C, we stay here. So they generate an nilpotent ideal, and hence they belong to the radical of H as an algebra. If we factor out this radical, what is left is 1 and C. This is exactly the group algebra of the group S2 with two elements. We are in the field of characteristic different from 2, so this group algebra is semi-simple. Which means that the elements X and Cx actually generate the whole radical. So they are in the radical, but now since the quotient is semi-simple, they generate the whole radical. So the primitive idempotents are then taken from this quotient, so they are 1 plus C divided by 2 and 1 minus C divided by 2. So for these two primitive idempotents, we have two simple modules. The module L plus, which is of course killed by the radical element X, and where C acts as the identity. And we also have the module L minus, killed by the radical, but where C acts as minus the identity. So this is the sign module for our group algebra. And we have the projective cover P plus of L plus. It has top L plus by definition, and then the socle is L minus. And this is because C and X, so the socle is obtained by the action of X, but C and X anti-commute. So the socle, the action of C in the socle will have a different sign than in the top. So the socle is L minus. And we have the projective P minus, which is a cover of L minus, and the socle of this projective is L plus. These both projectives have lengths 2. So now we can draw the quiver of this algebra. So we have the vertex corresponding to plus and the vertex corresponding to minus, and the two arrows from plus to minus and from minus to plus. And the relation is, of course, radical square 0 because projectives have lengths 2. So this is a radical square 0 Nakayama algebra with two simple modules. And it has finite representation types. And in fact, the simples and projectives, the four modules which we already listed, they are all indecomposable modules. The injective hull of I plus is P minus because P minus is the indecomposable module of length 2 which has socle L plus. So the injective hull of L plus is isomorphic to P minus, and the injective hull of L minus is isomorphic to P plus. So the trivial module in our monoidal category is L plus because the counit map sends C to 1 and X to 0. And so the module L plus is the identity object in our rigid monoidal category of all finite dimensional H modules. So how about describing the tensor product? So the tensor product of L minus with itself will be L plus. This is because the co-multiplication sends C to C tensor C, and it sends X to C tensor X plus X tensor C. So if we use the action of X, in both cases, the basis element here will be killed. And the action of C, we have the sign here, but these two signs cancel each other, so we get L plus. So in particular, the functor of tensoring with L minus is an involutive self-equivalence of H mod, because if we do it twice, we get the identity. So if we apply L minus, if we tensor it with P plus, we get an indecomposable module. And using exactness, we know that L minus tensor L minus gives us L plus. From this, it follows that L minus tensor P plus is isomorphic to P minus. And similarly, L minus tensor with P minus is isomorphic to P plus. And we can do it on both sides. So using exactness, we further compute that P plus tensor P plus is isomorphic to P plus P minus. So we just can write P plus as L plus on top and L minus in the bottom, and then apply both components to P plus, and use the splitness using projectivity. And similarly for tensor product of any P with any other P. Regardless which P we take, if we tensor them together, we get P plus P minus. And so we can even completely compute the Grothendieck ring. So in the basis of the Grothendieck ring, we have the classes of L plus, L minus, P plus, and P minus, and we have the following multiplication table. The class of L plus is the identity element. It does nothing. The class of L minus squares to the class of L plus, and it multiplies P plus to P minus and P minus to P plus. And the product of any P with any other P is P plus P minus. So we can now observe that this Grothendieck ring is in fact commutative, despite of the fact that our co-multiplication was not co-commutative. So this is a non-trivial observation, which is not very easy to expect from the data which we had in the beginning. So this is an example which shows how to take a Hopf algebra and, for example, how you can compute the Grothendieck ring of the category of finite dimensional modules over this Hopf algebra. So how this looks like. Okay, some problems and questions at the end. Question 1. Check with all details that the tensor product of A with itself with the multiplication M tilde and the unit map U tilde is an algebra. Question 2. Similarly, check with all details that the tensor product of a coalgebra with itself is a coalgebra. This should be coalgebra. Question 3. Check with all details the standard Hopf algebra structure on U of G. Question 4. Check with all details that the antipode axiom lifts adjunctions from K mod to H mod. And question 5. Compute the vector space dual of the Swidler's Hopf algebra as a Hopf algebra. Thank you very much and see you next time.